Hey, just another short video today, one on pH indicators, so things that change their color in different environments of H plus and OH minus. So just kind of want to walk through one in particular and then maybe briefly about another one. So what I want to talk about is how they work and why we use them in the way that we use them. They're in a lot of ways a lot more reliable than pH probes for a lot of situations. pH probes are notoriously finicky, expensive, and that's a pretty bad combination when something is both expensive and doesn't work the way you want it to. Indicators work essentially flawlessly. They're just sort of by their nature very easy to use, and the way that they work is actually through LeChatelier's principle. So let's say that we have an indicator, and the indicator itself is a weak acid, so we'll label it just HIN as a weak acid, and that weak acid can go through an ionization into H plus and IN minus. So let's say, for example, that we decide to use the pH indicator Methyl Orange. And I'm sorry for writing the word orange in blue. I don't have options of blue here, just black, red, blue, green, and yellow. So methyl orange is an actual pH indicator. It's red at a pH of 3.1 and changes its color somewhat gradually to be yellow at a pH of 4.4. And we'll come back to this, but its pKa, meaning the negative log of its Ka value, is 3.5, and that's important, as we'll see. So what happens is the HIN is red. So the weak acid form of methyl orange is red, and the conjugate base is yellow. And so we call it methyl orange because when they're mixed together, you're going to get an orange color depending on the ratio of the two things to each other. So how does this work to indicate pH? Well, if you kind of think about it, according to LeChatelier's principle, the more acid I add, so as you add H plus, well, the added H plus collides and reacts more often with the IN minus. So it's going to collide and reacts more with IN minus. And because it does that, IN minus goes down, and that causes the HIN to go up. And so that means I start removing yellow and getting more red. So as things are more acidic, you get more of a red color. And again, that makes sense given what we've got here. It's red at a pH of 3.1 or lower. And so the more acid that you add, the more it uses up the yellow conjugate base as they react together and form the red weak acid HIN version of things. The reverse would be true if you remove H plus or if you add OH minus. They're kind of two ways of saying the same thing. So if I remove H plus or add OH minus, so if things are getting less acidic, when you do that, you're basically removing a product. So the the IN minus has less to react with. So there's less H plus for IN minus to react with. So its reaction rate slows down. So reaction slows. So the HIN produces more IN minus. And when it produces more IN minus, you're going to get more and more yellow, and you're using up the red as you do that. So as things get less acidic, as you're using up that H plus, it goes away. The IN minus has little to react with, and you should be getting more and more yellow as the amount of IN minus goes up. So the indicators actually work pretty nicely, and almost all of the ones that are based on weak acids follow this essential idea, and so they work pretty nicely. They also work at different points of the pH scale. So this idea of pKa being 3.5 is significant because what it means essentially is that that's sort of the tipping point. If you recall, we've talked about this before. The pKa is 3.5 because that's the pH when HIN equals IN minus. So when those two are equal to each other, that means that H plus equals Ka. And so you can actually choose the indicator that you want for different titrations, because all you have to do is match up the pKa to the expected pH at the equivalence point. And you have a fair amount of tolerance here because of that steep part of the titration curve. You can be off by a point here or there on the pH scale, and it doesn't really matter because it only takes a drop here or there of your titrant to cause the color change. So if the pK is 3.5 and your pH at the equivalence point is 4.1, it's not going to make too big a difference. It's still going to turn that color. So you have a little bit of a tolerance. But the key idea simply is that you want to match the pKa to the expected pH at the equivalence point. That would be the thing that I would be very careful to sort of understand as you go through this. That's just a nice, easy way to do this. And they work sort of flawlessly. You guys have used phenolphthalein before in the lab. Phenolphthalein, unlike methyl orange, is a weak base. And so phenolphthalein, if we model that as the normal B for base plus water, making the usual OH minus and HB plus, well, we know that the characteristic color of phenolphthalein is that sort of fuchsia color. And as it turns out, its conjugate acid is actually colorless. So when things are acidic, in other words, when they're acidic and you don't have much in the way of OH minus, so if you have an acidic pH, that means that there's very little OH minus. And when there's little OH minus, it means the reaction moves to put it back, and you get a lot of HB plus. And that means it's colorless. And of course, the reverse is true when there's a lot of OH minus. When there's a lot of OH minus, it collides a lot with, it collides and reacts more with the HB plus, and that uses up the HB plus, and so you get less HB plus, and you get more B. So you get a lot less of the colorless substance, a lot more of the fuchsia substance. And you guys know from doing that lab in Chem 2, one drop can certainly make all the difference. I don't know that it matters a whole lot, although this is something that we briefly but not really carefully consider in Chem 2 because it's a little bit beyond the scope of Chem 2. But the pKa for phenolphthalein, let's pretend like I could spell that correctly on the first try, which I feel like I can. The pKa is 9.5. So technically that color change between fuchsia and colors happens around between 9 and 8. And we use it for a titration where the equivalence point is 7. So it's a little bit off in that way. But again, because of that steep curve, one drop sort of takes you somewhere between a pH of 6 and 7 and one around 8 or 9. So it's really not that inaccurate, but there are some other indicators that are a little bit closer to turning their color at 7 or 8. So the fuchsia color for phenolphthalein is around 10, and the colorless really kicks in around 8.3. And so somewhere in the middle is where you get that shift into that light pink color, as we well know. All right, just a little bit of information about indicators. I think it's interesting. It's a LeChatelier's principal idea that applies to acids and bases and a lot to titrations because, so I guess I mentioned, it's a lot easier to use one of these than it is to use a pH probe because you just add it and wait for the color change. Yeah, I know it's a little bit stressful to try to get exactly the color change you want, but it's a lot easier, trust me, than using a pH probe. All right, that's it for this video. We'll see you in the next one.